Okay, guys. Good morning. And good morning. Now, before I start, does anybody have any questions? Nope. Good. So let's see if we can get back on track. So, as we are still in chapter 10, we started with resolution. And what we mean is that the resolution simply just means is accuracy. Yep, okay. Well, the first resolution that we did was the EXA resolution, which we mean, yes, okay, said was ability to distinguish between two structures. Now, the way that we could say is, okay, what's going to be parallel to the beam's main axis, or we could say front to back, or more correctly, shallow and deep. Yep, okay. We said that, okay, this resolution here had a numerical value, which was half of your spatial pulse length. Yeah, okay. We also said that a low numerical value leads to a good exit resolution. Or let's just say it's okay resolution. That's going to be good. Whereas, okay, as a high numerical value will lead to a bad or poor resolution. Right. Okay. Now, please keep in mind, guys, that this numerical value here has to be, yes, okay, related to the distance between the two structures. Clear? Okay, so if the numerical value, let's see, if the numerical value is greater than the distance between these two structures here is okay, that will lead to a bad resolution. Whereas, okay, if it's the opposite, that the numerical value is lesser than the distance between the two structures, that will lead to a good resolution. Did you guys get that?
Yeah.
So, and please, 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 please make sure that you know that your axial resolution can also be known as the longitudinal resolution. It can be called range resolution. It can be called the radial resolution. And it can be called the depth resolution. Yep. Okay. And the unit of your numerical value is unit of distance. Just like, okay, yes, the unit by which we have, okay, measure the distance between two structures. It's also going to be, as okay, expressed in a unit of distance. Okay. Okay, guys. Now our next resolution. So this was just okay as a brief review for your axial resolution. Now the next resolution is going to be as okay, lateral resolution. Now here, yes, okay, again, yes, okay, resolution still means the same. We can say it's okay, the ability to accurately distinguish between, of course, that's okay, because that's okay, two structures. Now these two structures here is okay, what are they going to be? Now if you look at the word lateral, now can anybody recall the literal meaning of lateral? Anybody?
I mean, side to side, right?
Huh?
They're kind of side to side.
Or we mainly says okay on the side. Right, okay. Clear, okay. So here's okay, that's why it's going to, that's why it's called lateral. Okay, because it's going to be on the sides of the beam's main axis. Okay, so what would that mean? That, okay, yes, if you find this, okay, have a transducer. And guys, for lateral resolution, please, whenever it's okay, I draw the beam. Just assume as, okay, you're looking at the beam from above. Okay, so when I'm not going to draw the beam, yes, okay, when talking about lateral resolution, okay, to display, yes, okay, what it actually mean is that you mean is, okay, you should just assume that the diagram that I made is by looking at the beam from above. So that the beam is running down here, and we are looking at it from above. Clear? Okay. So right now, yes, okay, this is our transducer. And we can say, yes, okay, this is our beam. Right? Clear? Okay. So now when it says, okay, on the sides of the beam main axis, this is going to be as okay, the sides of the beam. For instance, because in all of this, yes, okay, this here, this was okay as the beam's main axis. Okay. So yes, okay, either side by side or on the sides of the beam main axis, or what we also can say is okay, will be perpendicular to the beam's main axis. Right, okay. Okay. And what does the word perpendicular mean?
Along
90
the
degrees.
length of it or the side of it.
Right. Perpendicular angle, for instance, was what we call a 90-degree angle, or we call it a right angle, right? Did that make sense?
Yeah.
Good. So again, what is it that we're going to do here? We're going to say, okay, that the dimensions of the beam, or we can say, okay, more accurately, the width of the beam is okay. Let's say this, okay, related to or compared to the distance between two structures on, yes, okay, in this case, either side of the beam, or it's okay, on the, which are perpendicular or at a 90-degree angle to the beam's main axis. Okay. Now, guys, just again, it's okay, beam anatomy 101. Because it's okay, we say it's okay, this was the transducer, and we had a beam. Now, please keep in mind, we are looking at the beam from above. We can say pretty much, okay, this was the beam. Clear? Okay. What did we call this area here? That was what we call the near zone. We could also call it the near field, or we could also call it the Fresnel zone. Clear? Okay. Whereas, okay, on the other hand, we had the far zone. We had, okay, yes, far field, or we have, yes, okay, the Fraunhofer zone. Did that make sense? What happened in the near zone? What happens in the near zone? The beam is getting narrower. Did that make sense? Well, okay, what happens in the far zone? What happened in the far zone is that the beam, the beam is getting, in this case, we can say it's okay wide. Okay, and in the entire course of the beam, what did we have? Okay, there was a point where the beam was at its narrowest. We call that the focus, or we call that the focal point. And what do we have at the focus or the focal point? The beam is at its narrowest. Did you guys get that? Did you guys get that?
Yes.
Yeah.
So let us just say, for instance, let's just take any number. We can say that, okay, yes, at this depth here, this would be, let's say it's okay, this will be the width of your beam, right? Okay, which, okay, yes, to begin with, yes, okay, it's going to be, yes, okay, we can say it's okay, the biggest diameter. Let's just say that, okay, this was 10 millimeters. Okay, what happens here? Yes, okay, the beam get narrower, so we can say, yes, okay, it may be, let's say, yes, okay, 5.7 millimeters. It gets even narrower, and okay, yes, at this point, yes, okay, it may get at its narrowest, which is going to be half of a millimeter. Okay, but these are going to be, okay, since we are looking at the beam from above, I guess it's okay, an aerial view of the beam, right? Okay. So what are these distances are going to be? These are going to be, okay, we can say they will relatively be the width of the beam. Did you guys get that? So they're going to be the width of the beam, which is going to be, okay, narrowest at the focus or focal point. Where, okay, what we mean is, okay, just see happens to the beam in the far zone is that, okay, yes, the beam is going to get wider and wider. So it says, okay, here maybe it's okay, 10.5 millimeters again, okay. As yes, okay, at this point, yes, okay, may get back to, yes, okay, 10 millimeters. Right, okay, which again, yes, okay, still would be the width of the beam. Did you guys get that? Okay. Now, for the lateral resolution, okay, this lateral resolution here is, okay, is going to have a numerical value. Okay. And the numerical value of your lateral resolution is nothing more but just going to be the width of the beam. Did you guys get that?
Yes.
Okay. Now, what can we say here? Yes, okay, as we follow the course of this beam here. So, what can we say? The width of the beam kept on changing, right? Right?
Yeah.
Okay. So, if the width of the beam keeps on changing, as the beam is okay travels deeper and deeper and deeper and deeper and deeper. Okay, your numeric is okay, your lateral resolutions or your lateral resolutions numerical value is not constant. Because here the numerical value was 10 millimeters. Here it was 7.5 millimeters. Here it was 5 millimeters. Then it goes back to 10.5 millimeters. Then it goes 10.5 millimeters, then it goes 7.5 millimeters, sorry. And then it goes 10 millimeters. And even, yes, okay, further now. Okay. Okay. So yes, okay, here, unlike your axial resolution, here, yes, okay, your lateral resolution is going to change. Clear? Okay. So the numerical value of your lateral resolution is nothing that needs to be halved or anything. Now, straightforward, the width of the beam is going to be the numerical value of the lateral resolution. This width of the beam here, as okay, was measured in a unit of distance. Because this width here is mean is okay, just the distance of 2 points which are side to side. Please keep in mind, guys, side to side, that will be the width. So you can say, okay, your shoulder span, that's going to be as okay, the width. That's an example of width from side to side, right? Did that make sense? Clear? Okay. So here, yes, okay, what's going to be and you, of course, that's okay, you'll measure this here in a unit of distance. Okay, you're not going to say, it's okay, it's 22 kgs or 55 pounds or 72 degrees Fahrenheit or something like that. Okay, this is a distance it's going to measure using a unit of distance. Did that make sense? Okay, but that width of your beam, that is going to be directly, yes, okay, your numerical value for the lateral resolution. Did you guys get that? Any questions so far? So here it is not your pulse, not your spatial pulse length or anything. No, it's got simply, yes, okay, the width of your beam. Okay, guys? Now, in the entire course of a beam, let's put it this way. Or let me just write it. In the entire course of a beam, where does it have the lowest width? Yes, guys.
The focal point?
Very good, Teresa. Exactly, at the focal point, right? Okay. Okay. So that's going to be as okay at the focal point, or as you can say, it's okay at the focus. Did that make sense?
Yeah.
Good. So we can say it's okay due to this lowest width here, right? Clear? Did that make sense?
Yep.
Due to this lowest course or lowest width of the beam at the focus or at the focal point, then this is also going to be the point where the lateral resolution has its lowest numerical value, right? At the focus. If this was the point and the entire course of the beam where it had the narrowest width. Right, okay. Then we can say, okay, that's also going to be the point where the lateral resolution is going to have the lowest numerical value. This was your beam, right? We said here, let's just say it's okay, 1 centimeter. Here, 0.75 of a centimeter. And it's okay here at the focus. We had a depth of, or we had a width of half of a centimeter. What did these numbers here represent? Mainly it's okay, just the width of the beam, right? Right?
Yeah.
Good. So at which point did we measure the narrowest width of the beam? At the focus. And what did we say that the numerical value of the lateral resolution was? Nothing more but just the width of the beam. So here is okay, it was highest. It just got lower and lower until we reach the focus where the beam reaches its narrowest width. And say yes, okay, the narrowest width is going to be at okay, the lowest numerical value of your lateral resolution. Did that make sense? Whereas, okay, as far as a part of this here is okay, we can say, okay, this would be as okay, where we have the greatest width of the beam, right? Right? At this point here. Is where we have the greatest width of the beam. So since that's going to be the greatest width of the beam, that's going to be as okay, where the numerical value of your lateral resolution is at its max. Did that make sense?
Yes.
Okay. Of course, yes, okay, it will also get greater and greater and greater as we go into the far zone where you can say, okay, what's going to happen here is that there will be an increase in the numerical value, even in the far zone. Whereas, okay, in the near zone, what happens? There's a decrease in the numerical value because it starts from bigger to lesser, gets the least at the focus. Did you guys get that? So here,
Yeah.
yes, okay. Whatever the width of the beam is going to be the numerical value of your lateral resolution. That width of the beam is going to be measured in a unit of distance. Okay, or it's going to be expressed in using a unit of distance or length. Clear? Okay. Now, just like in your axial resolution, nothing really changed. The only difference was that, okay, for your axial resolution, it was half of your spatial pulse length compared to the distance between two structures. But in axial resolution, that was going to be as, okay, shallow and deep, or front and back, all parallel to the beam's main axis. Clear? Here is the diameter or the width of the beam. Okay, it's going to be the width of the beam that now is going to be as, okay, related to two structures, or the distance between two structures which are perpendicular or at a 90-degree angle to the beam's main axis. Or as we can say, it's okay, on either side of the beam. Clear? Okay. Okay. Did that make sense? So what did we say previously? Now where we have a great numerical value of the lateral resolution, like a point here. Okay. Or we can say a great numerical value, that's okay, most likely will lead to a bad or poor resolution. Whereas a low numerical value of a lateral resolution most likely will lead to a good resolution. Because at this point here, where we have, yes, okay, the greatest width of the beam, which was 1 centimeter, right? Right?
Yeah.
Good. That will mainly mean that, okay, as for us, if we, for instance, okay, at this point here, okay, want to have a good resolution, that the distance between structure here and structure here has to be 1 centimeter or more. That the distance between this structure here and here has to be 1 centimeter or more than 1 centimeter apart from one another for us to be able to, yes, okay, see them as two separate structures. Did that make sense?
Yeah.
Okay. which is, well, okay, down here, for instance. Even if the structures are just half a centimeter or 5 millimeters apart, you will still, yes, okay, see them as two separate structures. But if similar distance was here, 5 millimeters, 5 millimeters, this was going to give us a bad lateral resolution at this depth here. Because here's okay, the beam's distance was greater, or the width of the beam was greater, or more accurately said, the numerical value of your lateral resolution was greater than the distance between the two structures which still were side on side, or parallel to the beam's main axis, or perpendicular, sorry, to the beam's main axis. Did that make sense? So what we mainly can say is that a greater numerical value, here we can say, okay, of the lateral resolution most likely going to give us a bad lateral resolution. Whereas on the other hand, if we say a no numerical value of a lateral resolution is going to give us a good lateral resolution. Yeah, okay. And where is it that we have the lowest numerical value of the lateral resolution? Is at the focus or focal point. Yeah, okay. That's going to be the point in the entire course of the beam where, yes, okay, the beam has the narrowest width. Okay. This narrowest width here is now going to, yes, okay, just be translated as, okay, as the lowest numerical value of your lateral resolution. And this is going to be, yes, okay, the point where, yes, okay, in an entire beam, yes, okay, that we actually, yes, okay, will have the best lateral resolution. Okay, but this numerical value of a lateral resolution, which is the width of the beam, still has to be, as okay, related or compared to the distance between the two structures. So we can still say that as far as, okay, the numerical value of here is, okay, we say the lateral resolution, if that, for instance, okay, is lesser than the distance between two structures, and now, yes, okay, these are going to be, yes, okay, which are side by side. Okay, when the numerical value is greater than the distance between the structures which are side by side, this will lead to a bad resolution. In this case, it's okay, which resolution? Lateral resolution. Whereas, guys, if we go opposite and say that the numerical value of lateral resolution, which we know is, okay, is the width of the beam. is greater than the distance between the two structures which are side by side, that is going to lead to a good lateral resolution. And what was a good resolution? That those two structures are accurately displayed or correctly displayed or distinguishably displayed as two separate reflectors or structures, right? Whereas a bad resolution will mean that two structures may appear as one smush. That you really can't distinguish that, okay, here's one thing and here's another thing. But that they actually appear as one mess. Or we see them as one single structure. Okay. So it's me, it's okay, just a matter of, okay, how many fingers? Clear? Okay. If you say it's okay, one, then okay, that's a bad resolution, right? It's not accurate. Either you don't know how to count, or yes, okay, you're having a problem focusing on these two fingers here. Clear? Okay. Likewise, that's okay. If I do this and you say two, then okay, it's still not right. Clear? Okay. You go like this, you say five, you say three, well, okay, it's still not right. Did that make sense? Clear? Okay. So that distance, or you can say it's okay, the width of the beam has to be compared to the distance of between the two structures. But yes, okay, here these two structures are going to be side to side, not front to back, side to side. Clear? Okay. The ability to distinguish as okay, two structures which was front to back, or let's do this, shallow to deep. That was what we call the exit resolution. And what determined that? Half of the spatial pulse length. Did you guys get that? Any question, guys? Yeah, okay. So let us just take a beam, for instance. Oh, sorry, not a beam. Let's see. Okay, yes, okay. Your transducer, we have let's say that, okay, let's see, what do we have here? We have structures. And we see that, okay, yes, they are placed LSS, okay, at equal distances. Okay, now what are they going to be? Well, okay, this is going to be, okay, our beam's main axis. Okay, but let's just say that, okay, as throughout, as okay, the distance between this structure and this structure, this structure and this structure, this and this, this and this, this and this is the same. Let's say that, okay, this distance here is half of a centimeter. Did you guys get that?
Yeah.
Good. Now we have our beam. And yes, okay, guys, our beam starts like this. for instance. Now, what we can say here is that, okay, yes, at this point here, it's okay, the beam's diameter may be, let's say it's okay, 0.8 of a centimeter. Here is going to be, let's say, okay, 0.6 of a centimeter. Here, we can say, okay, it's 0.4 centimeter. Again, it's okay, here it is 0.6 centimeters. And here again, it's okay, let's say it's okay, 0.8 of a centimeter. Okay, so these values here were our numerical values of the lateral resolution. Whereas throughout, we can say, okay, this depth here is okay, or these distance, we just kept assumed that, okay, yes, that they were equally distant from one another. But this was going to be as okay, the distance between two structures on side to side of the beam's main axis. So what do we see here? The numerical value of your lateral resolution is greater than the distance between the two. So this is going to be a point where you will have a poor lateral resolution, and these two structures here is okay, may appear as one big mass like this. Likewise, here is okay. We still have a greater numerical value and of the lateral resolution and a lower distance between the two structures. So here's okay, these two structures which were physically as okay, two separate structures, but they are going to appear like this. Whereas here, the numerical value of our lateral resolution is lesser than the distance between the two structures. So that's okay. These two reflectors here are going to appear like this. So the same just goes here as well. Okay. That here is okay. What we have is we have a greater numerical value compared to it's okay a lesser distance. So again, a poor lateral resolution. Whereas again here we have a great numerical value and a low distance between the two structures. And again, it's okay, we will have a poor lateral resolution. Did you guys get that?
Yeah.
Okay. Whereas this distance here, between, let's say, it's okay, this structure and this structure, or even it's okay, this and this, or we can say it's okay, this and this, or this and this, or this and this. Okay. That should be compared to half of the spatial pulse length, and would determine whether we have And that would determine our exit resolution. So if this distance, for instance, okay, was the distance between the two structures, shallow and deep, shallow and deep, shallow and deep, was greater or equal to half of your spatial pulse length, and that will give us a good exit resolution. Because the numerical value just happens to be lesser than the distance. Whereas if it was opposite, that the spatial pulse length was greater than the distance between, yes, okay, the structures, then that would give us a poor exit resolution. Did you guys get that? So two people sitting side by side. If I'm not able to, yes, okay, distinguish them from one another, that will be a poor lateral resolution. Clear? Okay. Whereas, okay, if I'm not able to distinguish two people, one sitting in the front row, while the person sitting in behind him or her, that will be, okay, a poor exit resolution. But the exit resolution is determined by your spatial pulse length, or half the distance of your spatial pulse length, whereas your lateral resolution is going to be determined by the width of the beam. Did you guys get that? Okay. And as I showed yesterday, because some of you will then say, okay, that does mean that, okay, yes, we will only be able to focus at one single depth. No, I showed you the image. Okay, we kept, of course, that's okay, we have to keep it, that's okay, bring it to that depth because that's okay, 7 centimeters. But in this entire thing, again, okay, this. We can say, it's okay, we are able to just, okay, focus at this depth here, right? You're also able to just, okay, focus at this depth here. Even just, okay, at the same time. So when it, for instance, okay, focus at what we can just call is, okay, focus 1. What did that mean? That may mean that, okay, this depth here is, okay, that was going to be the point where the beam will be at its narrowest. Okay, where, okay, as when we focus at this depth here, or we can just call it, okay, focus 2. Okay, which was this depth. What did that mean? That there was going to be the point where the beam would be at its narrowest. Did that make sense? Clear? Okay. So your system actually is, okay, enables you to focus at more than one point at a time. Did that make sense? Clear? Okay. What's the plus point of that? What's the plus point of that? That you'll be able to get, okay, as better lateral resolution at more than one depth. Clear? Right, okay. What's the negative point of that? Well, okay, let's not talk about the negatives yet. Okay, but that's okay. It also has okay. There's always going to be okay another side of the coin. Okay, so that's where it's okay your relations comes in. So let me just ask a question indirectly. The point where you have your lowest numerical value of lateral resolution is also the point where you have the highest dash.
Frequency?
My dear, why does your frequency change? Does your frequency change as the sound beam travels?
No.
No. Okay, good. So what did I say? The point where you have the lowest numerical value of your lateral resolution is the point where you have the highest dash.
Intensity? Intensity?
Here we go. What did you have at the focus? The beam was at its narrowest, right? Right? And what did we say? That was the point in the entire course of the beam where the beam has its highest intensity. Good job, Chris.
Thank you.
You're welcome. Okay. I just flipped it a little around here and says, okay, lowest lateral resolution, lowest numerical value of lateral resolution. Or where do you have the lowest numerical value of the lateral resolution is at the point where the beam is at its narrowest width. Did you guys get that? Good. Okay. So what we actually want for a good lateral resolution is, okay, we can just clear this out. What we mean is, okay, want for a good lateral resolution is that the distance between two structures which are side by side, that this distance here is greater than, let's say it's okay, the width of the beam. If that's the case, you will have a good resolution. If it's the other way around, that this distance here between two structures which are side by side is lesser than the diameter of the beam, which means okay, would be the okay, yes, if we say that we had two structures like this, Okay. And the distance between them would be this. Or whereas, okay, the width of the beam is greater than that. That will lead to a bad resolution. Or just think of it in this way. That you see a door. Okay. This is going to be as okay the width of the door. And let's say it's okay that this is 20 inches. Now, as far as, okay, yes, your shoulder span is 20 inches or less, you'll be able to pass through that door with no problem. So we can say, okay, a good passage through the door, right? Right? Whereas if we had the same door, let's say it's okay, 20 inches. But that your shoulder span was, let's say it's okay, 42 inches. Or anything greater than 20. Well, that'll lead to a bad passage. Because you either had, yes, okay, shrug your shoulders or try to go sideways or whatsoever to be able to pass through that or walk through that door. Did that make sense? So to be able to just, okay, pass through a door without any problems, that would be just, okay, a good lateral resolution. Whereas, okay, if you had to shrug your shoulders or do any, yes, okay, other crazy maneuvers to pass or walk through that door, because your width is greater than the width of that door would be, or lead to a bad lateral resolution. Did that make sense? So you just want the numerical value to be lesser than the distance between the structures. That would be good. If it is greater, then that will be bad. And that applies for both your lateral resolution and axial resolution. Any questions? Nothing? Good. Last but not the least, the nicknames or the akars of lateral resolution. Now, it doesn't have as many nicknames or it's okay synonyms as your axial resolution, but okay, yes, they still have a few. Now, just look at it in this way. This was our beam. We can say, okay, this here is okay, was the beam's main axis. So at least one of the words or two of the words or nicknames has okay make sense. Let's say it's okay that these were our structures here. For instance, okay. And what we see is that okay at that day it's going to be it's okay perpendicular to the beam's main axis. Or side by side, or side on either side of the beam's main axis. Now what we said was that the word lateral literally meant yes, okay, on the side. So that's all I can yes, okay, the lateral resolution. They also use the it's okay, it's also going to be called the angular resolution. Yeah, okay. Now since we said that okay, yes, they are perpendicular to the beam's main axis. What is going to be the relation between the structures and your beam's main axis? Transverse. So that's why it's okay. You can say it's also called transverse resolution. Now, guys, I know the last one is a pain in the butt. Azimuthal resolution. Now, I may know a lot of things. Likewise, it's okay. All of you may know a lot of things. But I'm not going to claim that I know, yes, okay, what the word azimuthal would mean. So I looked it up. Okay. I looked it up, and this is mainly as okay, something as okay, a term that they used for as okay, talking about angles between stars. And I said, okay, let's do that one for NASA or something like that. Oh, that's okay. The people who do the horoscope. But that's okay. Unfortunately, it's okay, since it's written in the book, you have to remember it. Okay, so the formula or the mnemonic for your lateral resolution is leta. Okay. Or you can say, okay, I don't want leta, I want it to be tala. That's fine. Doesn't really matter. As long as you're able to remember that lateral resolution is also called angular, it's also called transfer, it's also called azimuthal, I'm good. Right, okay. What would be another name for your range resolution? Or what are the other names for your range resolution?
Axial.
And
Oh, you want all of them?
I think so, yes.
Longitudinal, axial, radial,
Uh-huh.
range, like you said, and then depth.
Depth, exactly. Okay. Okay, guys, so here it's all a matter of width of the beam compared to the distance between the structures side by side. That width of beam, as we know from the anatomy of the beam, changes. In the first part, it decreases. In the later part, it increases. Okay, so the entire course of the beam where we have the narrowest width is at the focus. Did you guys get that? So your lateral resolution does not remain constant. Okay, the axial resolution, that's okay, remain constant. Don't go and say, okay, now, but what about the wavelength that changes? Because what we talk about here is mainly going to be as okay, the spatial pulse length of the pulse at the level of as produced by the transducer. That's what's going to determine the axial resolution. So what is the spatial pulse length of the pulse produced by the transducer? Clear? What determined that? That is determined by number of cycles and the frequency, which then determine the wavelength. Inversely, right? Okay. Okay, guys. Now, so far, yes, okay, these were your two resolutions, or two of the couple of the resolutions that we'll be talking about. Okay. So just take a short while, read a little bit about the lateral resolution. Oh, that's okay, the 2-3 pages that we just did. And what the hell can we say is on page 150, on page 153, yes, okay, you may see it's okay, a comparison between axial resolution and lateral resolution as a summary. Please read on that as well. And any questions you have, yes, okay, you can ask when we return back. So I see you guys around, should we say 10:40? Okay. Okay, guys. Back. Now, did you guys get the chance to get the chance to to read on your two resolutions? Okay. Any questions? So far, are they clear? Good. Now, guys, let us just go on to our next main topic. Which is going to be focusing. While focusing mainly means, okay, we can say it's okay, it's going to be the process of reaching to focus. Now, what was your focus? Focus or focal point, let's put it say. What was it that these here were? The narrowest point in the beam. And what we said earlier today was, due to this, highest intensity, to be more specific, spatial intensity. We can also say that, okay, let's add the focus, which is, okay, as the narrowest part of the beam. That's where we have the lowest numerical value of lateral resolution. And due to that lowest numerical value of the lateral resolution, we can say that the lateral resolution is best. Okay. But the whole point of focusing is mainly as okay a matter of bringing the beam to its narrowest point. But your point in this course where it is at, where it's become narrowest. Okay. Now that may be as okay a little bit of an issue because okay, as we know, sound waves mainly as okay travels in straight lines. Mainly speaking, yes, okay, sound waves travel in straight lines. So if they travel in straight lines, okay, how would they be able to converge all together and reach a narrower point, which will be the focus? That's what we mean is, okay, we'll just briefly talk about today. Because, okay, a whole grade or a whole part of this focusing is going to be brought back. It's going to just, okay, be discussed again is okay in chapter number 12. Okay. Now, as far as focusing is concerned, now I know that your books talks about 3 methods, but we're going to just, okay, mainly as, okay, do it this way, and we can see focusing is going to be as, okay, mainly of 2 major methods. Let's say 2 types. One is going to be as, okay, what we will call fixed focusing. The other one is going to be as, okay, what we will actually as, okay, call later on, we will say it's okay array. But which mainly as, okay, will mean that we have multiple focal points. Okay, and this type of focusing here mainly is going to be as, okay, what we'll call electronic. So this is going to be as okay an electronic focusing. Is that clear? Okay. And the juicy details about this electronic focusing here is okay, it's okay, one of the major things that we will come across in chapter number 12. Did you guys get that?
Yes.
Now, guys, when we say it's okay, fixed focusing, that means it will mean that okay, yes, we can say it's okay that we only have so there's going to be one focal point, not what we have here as which were multiple focal points. The other dilemma about this one focal point here that okay, yes, is that it is fixed to a, let's say as okay, specific depth. Okay. So if you look at this in an image, we say as okay, that this was the image that we had. You can have, okay, so you can increase the depth of the image. That's not the question here. But no matter what depth you keep the image at, well, okay, yes, there's only going to be one focal point. And let's say it's okay, in our instance, yes, okay, this focal point is here. Or that's the single focal point that we have. And this is going to be as okay, fixed. Which mainly means that, okay, yes, in this case, yes, okay, we don't have the liberty of being able to move it to a shallower depth or greater depth because it was fixed. Okay, and it was also just going to be one focal point. Clear, okay, which mainly means that, okay, yes, since it was just one focal point, yes, okay, we were not having the liberty of increasing the number of focal points along our depth of the image. I say, okay, we want to focus at not just this point, but also at this point here. And not just this point, but also at this depth here. Okay, so all this, okay, so this fixed focusing here is what we also, yes, okay, were referred to as, sorry, this fixed focusing is what we also will call, generally, yes, okay, we'll call it mechanical focusing. And or it can also be referred to as conventional focusing. Is that clear? But the thing to remember about is, okay, what we call fixed focusing is going to be one focal point. Clear, okay, and that focal point is fixed. That focal point is fixed. All determined by us, okay, the make of the transducer. Okay, so all dependent upon, you can say, okay, the shape and size and so on, so on, so on, so that they use of the PCT and things like that, that they use to produce that transducer. Those will determine the focal point of that transducer which is going to be fixed. So a thing which is fixed means that's okay that you cannot adjust it. Right? Have any of you ever been to a flea market or not necessarily a flea market, or where you actually is okay, may be able to bargain about the price? Good. Just try to bargain about the price in Walmart or Macy's or J.C. Penney's or something. They'll say, okay, the price is the price is fixed, right? Okay, $22.99. Well, okay, that's what it is. You want to pay this much for it? Okay, yes. Here's a pair of trousers or a pair of socks or whatever, or a jacket or whatever. Give us the money and take it. If not, then okay, just leave it here and okay, have a nice day. So that's fixed, right? Okay, you can't say, okay, would I be able to pay $12.99 for it or no? Clear? Okay. Did that make sense? So fixed and it's one price. Not a penny more, not a penny less. So here is okay, the focal depth is, or focal point is fixed. And it's only 1 point. Now our main issue was in this case that we said, okay, is we know that sound wave travel in straight lines. So if something travel in straight lines, that's okay. How will we be able to cause it to just okay move like this and merge onto a common point, which is going to be narrower, which we'll call the focal point. Okay, guys, so as far as, okay, you're fixed. Oops, please don't do that with me. Fixed focusing is concerned, guys. That's where we have two types of fixed focusing. There's going to be, it's okay, what we will call internal focusing. And just so you guys know that, okay, yes, this internal focusing here is still going to be fixed. The other type is going to be external focusing. And just so you guys know that this external focusing here still is going to be fixed. Did you guys get that?
Yeah.
Good. So internal focusing and external focusing is both going to be examples of fixed focusing. Let us just look at it. Now, what does it mean to have an internal focusing? So in case that we see it's okay, internal focusing. And that's less okay, we say it's okay, external focusing. And both of these here is okay were fixed and fixed, sorry. Now, as I said earlier, it's okay, this is meaning that's okay going to be determined all by the make or the construction of your transducer. Okay, that will be actually it's okay, will be able to, it's okay, set that focal point, which is going to be fixed. So in the transducer, yes, okay, what did we have? We can say, yes, okay, we have the PCT. Let's just use the colors in the book so you guys can see. It's okay. We can say, it's okay, we have the PCT. We may even, okay, also have the backing material. But what we as okay will have in case of internal focusing. Internal focus is that okay, yes. The surface of your PCT curved surface of the PCT. Okay, very mainly says okay, well we had the electrical signal, yes, okay, it travels, so it becomes sound waves. Okay, but it's okay as it hits this curve here. That's going to mean yes, okay, this curve surface here is actually going to cause it to. It's actually going to cause the sound waves to refract. And as a result of that refraction, that will mainly, in this case, I call that, okay, yes, they will start to converge to, yes, okay, reach a focus. Did you guys get that?
So the curved surface of the PCT causes sound waves to refract and converge to reach a focus.
Exactly.
Okay.
Have you ever seen a magnifying glass? Now, a magnifying glass, if you look closer on the surface, those are not straight. Or even as okay, if you look at your glasses, those of you who wear glasses, if you're not, look at the glasses. You'll find that the glasses are not going to be straight. Okay, the surface of the glass may be straight, but okay, that's still going to be as okay a slight curve in it. And what is that going to cause? Refraction. But for your glasses or magnifying glass, that's going to be as okay refraction of light. But it's the same concept. Did that make sense? So what can you say here? Or you mainly can say here is okay, there's all going to just okay. The focal depth for this transducer here is mainly going to be as okay related to as okay the degree of curvature of the surface of the PCT. That may cause okay as that the beams as okay merge onto a common point at a shallow depth, or merge onto as okay a common point, let's say as okay at a greater depth. Okay, but that will be as okay the focal point of this transducer here, which was fixed all determined upon the curvature of the PCT. But guys, mainly because it is the surface of the PCT itself that is curved. That's why we call this internal focus. Did you guys get that?
Yeah.
Good. Whereas if we say external focusing, okay, now it says, okay, we had, okay, as our backing material. Now here we have us, okay, our, we can say it's okay, PCT like this. Or crystals as you know it. Now, here, yes, okay, they call it, yes, okay, external focusing. Because externally to the PCT is there going to be a lens. And here, yes, okay, is going to be, yes, okay, the surface of the lens here. Let's just do it this way. This lens here, yes, okay, what does that have? That has a curvature. Or it has a curved surface. Clear? Okay. Okay. Of the lens. And pretty much, okay, it does the same as, or okay, either the lens in your eye would have done, or yes, okay, the lens in your glasses. Or as a matter of fact, yes, okay, the lens in a camera would do. Refract those waves and cause it to, yes, okay, reach onto a focal point. Did that make sense?
So the internal focusing has a curved surface of PZT and the external has a curved surface of a lens.
Exactly.
Okay.
That is placed, well, okay, we can say it's okay. It stays, okay, built into the PC, into the transducer, right? Okay, because here, in both cases, it's okay, that's where you will have, it says, okay, that will be your matching layers. Clear? Okay. But both of these here is okay, were examples of fixed focusing. The only difference here is, the only difference between the two is that, okay, as an external focusing, sorry, it's a lens in the transducer with a curved surface that's going to cause the beams to, or that's going to cause the sound waves in this case is okay to refract and cause them to focus at a specific point at a specific depth. Yeah, okay. Whereas in internal focusing, it was the surface of the PCT itself that was curved that will cause the beams, or sorry, the sound waves to refract to focus at a point, and this point here was going to be fixed. So both of these two here have fixed focal length. Fixed focal length or depth. Which mainly means that, okay, yes, we don't have the liberty of what we did yesterday. Move the focal points up and down. Clear? Decrease it to a shallower depth, or yes, okay, move it down to a greater depth. Clear, okay? And there was only one focal point, so we cannot set 2 focal points, we cannot set 3, we cannot set 4, or 5 or 6 or whatsoever. Did that make any sense at all? Yes, ladies and the gentlemen.
Yeah.
Right, okay. So looking at that, yes, okay, what kind of transducer is it that we are using in the lab? An array transducer. Clear, okay, because it is going to, yes, okay, enable us to focus at more than one point. Did that make sense? So if a transducer enables us to focus at more than one point, well, okay, that point can't be fixed. You can't say that, okay, as all trousers in JCPenney is okay, go under a fixed price, which is $22.99. Clear, okay? You may find trousers that may cost $42. You may find trousers that cost just $12. You may be lucky enough to find something that only costs you $2. Clear? Did that make sense? Okay. So transducers where we have more than one focal point, or will be able to focus at more than one focal point, those transducers will be referred to as array transducers. Whenever you see the word array, A-R-R-A-Y, mainly will mean multifocus. Did you guys get that? Okay, now the question arises, well, okay, isn't that transducer also made by a manufacturer in a specific way? Certain size and shapes of PCTs and things like that. Of course they are. So how in the blue will we be able to focus at more than one point? Or even if you just keep one focal point or a single focal point, but it's okay, be able to move at that up and down to shallower depth or deeper depths. That is mainly because it's okay for your array transducers. In 99% of the cases, that the focusing is electronic. So it's more complex, or there's more, as okay, you can say, it's okay, technique or mechanics, or as okay, actually electronics behind it that enables the system to be able to, or your specific transducer to be able to focus at multiple points. Yeah, okay. How do we send those commands to the system? That's what I showed you guys yesterday. By changing or adjusting focus numbers and focal positions. Did that make sense? Okay. Now, guys, the juicy details of this electronic focusing. The juicy details of electronic focusing is one of the major things that we will talk about in chapter number 12. Is that clear? Any questions? Okay. So what happens when a beam focuses? What happens in the near zone? What happens to the beam in the near zone, guys? Come on, please. Somebody say something.
Converge.
Huh?
It converges.
Converges are, in easier words, it narrows down, right? Okay. Okay. So that's one of the main modification or changes that happens in the beam that causes focusing. Yeah. Okay. What happens to the beam beyond the focus? Or deeper than the focus?
It widens.
It widens or diverges, all right? Okay. Clear? Okay. Now, what they mainly say is that, okay, what happens is, okay, as you focus a beam is that the focal point moves closer to the focus, which mainly mean, what would that mean? That the focal length decreases. Okay. And last but not the least is that at the focus or at your focal point is going to be where the beam is at its narrowest. Okay. Well, that's okay. As far as these four consequences are just okay, or it's okay. More consequences, modifications of beam is concerned, don't really need to worry that much about it. If you know your anatomy of the zone of your what the hell we call that fellow beam, you should be good. If you know it's okay, how frequency and PCT diameter is related to focal depth or focal length, you should be good. If you know how PCT diameter and frequency is related to beam divergence and far zone, you should be good. Okay, as far as the beam is concerned, if you now know that, okay, as beam diameter equals, or width, sorry, let me not use the word diameter, that beam width equals lateral resolution, you should be good. If you know that spatial pulse length, or half of the spatial pulse length equals axial resolution, a numerical value of axial resolution, you should be good. If you know the nicknames for axial resolution and lateral resolution, you should be good. If you remember that your axial resolution remains constant, whereas, okay, as lateral resolution changes because of the numerical value of the lateral resolution changing because of the changing width of the beam, you should be good. Did I make myself clear? And it's okay if you know that fixed focusing is external and internal. That fixed focusing is internal and external. And that multi-focusing or electronic focusing is going to be multi-focusing, or we also can call this, okay, array focusing. You should be good for now. The juicy details of this, we will talk more about that when we get to chapter number 12. Yeah, okay. The width of PCT is going to just, okay, play a role in determining the width of beam at focusing, at the focal points. And if you know that fixed focusing is internal and external, you can say, that's okay, internal is, that's okay, what we are looking at right now if you're not wearing glasses. External focusing can be, as okay, an example of you as okay, only be able to focus if you wear glasses, if you need glasses. Or what is it that you do when you wear glasses? What does your glasses have?
Lens.
A lens. Right, okay, so an external focusing, what did we use? We had a lens. Did that make sense? Okay, so external focusing is okay, it's just like okay, wearing glasses. Internal focusing would have been not wearing glasses. Okay, but yeah. Now, my dear students, there is a total of 15 questions at the end of this chapter here. Right? Okay. I can give you guys 25 minutes to try to answer these questions on your own. And then we can come back and look at them. Does that sound like a deal? Okay, guys, now call up the answers. You may have to look at, okay, yes, figure 10, 11 to answer for some of the first, yes, okay, questions here. Okay. Now, so far, any issues? Nope. Okay, dear. Let's try to see. So I'm just going to just, okay, try to reconstruct our diagram here. 9 millimeters. And we can see as okay, we have the beam here, which is going to be And we can say, okay, this depth here is 8 centimeters. Did you guys get that? Yeah, okay. Now our first question is, in this case, is okay, yes. Okay, yes, what is the lateral resolution? At a depth of 8 centimeters. Okay. Now just so you guys curious, okay, this 8 centimeters is what the data tells us. That's going to be okay, the focal depth. Okay. So what would they mean by the lateral resolution? What do we mean by lateral resolution here? The width of beam at the focal point, which is going to be at a depth of 8 centimeters. Which will be as okay, what will be the width of the beam here? Okay. Then okay, yes. Here's okay, the width of the PCT was 9 millimeter. Here is just going to be half of the 9 millimeters, which is going to be 4.5 millimeters. Did you guys get that?
Yeah.
Okay. So yes, okay, this chapter here is okay if you don't understand, or at least that's okay, lateral resolution. If you didn't understand your beam, yes, okay, you may not be able to, yes, okay, totally, yes, okay, understand this. Our question number 2 then just ask us, okay, yes, what is the lateral resolution at a depth of 16 centimeters? Which means, yes, okay, just for me, 16 centimeters, that's going to be, okay, you have 8 centimeters here and another 8 centimeters here. And what was it that we said? That this point is okay, which is going to, yes, okay, now this is going to be a total distance of 16 centimeters. And it's okay, the beam is made, it's okay, just going to diverge out to become the same 9 millimeters width. Then we can say, okay, this distance here. That'll be the width. But that actually, that's okay to mean that at this point here, it's okay, we have to have at least that the distance has to be at least 9 millimeters apart for them to be distinctly shown. Did that make sense?
Yes.
Good. Now, next question here. All questions, okay, the width of the beam, width of the beam, width of the beam was just replaced by lateral resolution. So question number 3 asks, that's okay, what is the best estimate for the lateral, for the resolution at a depth of 4 centimeters? Which is, we can say it's okay, 4 centimeters. Let's say it's okay, it's here. Okay, so me, it's okay, just asking, it's okay, what will be the supposed width of the beam at this point here? Okay, now we will not be able to just, okay, accurately say that. Okay, but the one thing that we should be able to say is that it's going to be a number. This is going to be as okay, at least less than 9 millimeters, but it will be greater than 4.5 millimeters. Okay, because what had happened? Well, okay, yes. From here to here, yes, okay, the beam had converged from 9 millimeter to a smaller diameter. Okay, and from here to here, yes, okay, will still converge or narrow further from this smaller diameter compared to, yes, okay, the 9 millimeters to a diameter of 4.5 millimeters. So any number that falls in between 9 and 4 is going to be your answer. So 1 centimeter cannot be, because 1 centimeter is going to be greater than 9 millimeters. Actually, it's okay, 1 centimeter is 10 millimeters. It can't be 9 millimeters because that would have been, yes, okay, the width of the beam here. Okay. It could be 5 millimeters because, okay, 5 is lesser than 9 millimeters, but it is greater than 4.5. It can't be 14 millimeters because that would be, it's okay, yes, probably it's okay, the diameter of the beam out here. Okay, there the beam actually is okay, had diverged more than, okay, where it was here. Did that make sense? So the main sheet here is that, okay, it's okay, there's okay, it's somewhere it's okay in the focal depth. We haven't reached the focal, so it's going to be greater than the, or lesser than the diameter of the PCT, but lesser than the diameter of the beam at the focus point. Okay, so any number that falls or fulfills the criteria of being lesser than 5, or lesser than 9 and greater than 4.5, in this instance here, it's okay, it would have been the correct answer. Did you guys get that?
Yeah.
Good. Question number 4. Now the main yes, okay, just asked the very same thing, but it's okay, here they go by 7 centimeters. And again, yes, okay, guys, we will not be able to, yes, okay, accurately say what the diameter should be or would be. But one thing that we can say is okay is that it's going to be lesser than 9 millimeters and still greater than 4.5 millimeters. Okay. And since we're not able to, yes, okay, exactly say, that's why it's okay to say the best estimate. So it's the same options. So again, yes, okay, 5 millimeters is greater than 9, or lesser than 9, sorry, but it's greater than 4.5. So 5 millimeters is your right answer here as well. Did you guys get that?
Yes.
Good. Yeah. Okay. Now the next question, question number 5. Ask, what is the best estimate for the lateral resolution at 20 centimeters or 21 centimeters? Clear for me, is okay, that's going to ask, okay, that's what will be the width of the beam at a depth of 21 centimeters. Let's say this because this was 8. Another 8 would be 9 or 16 centimeters. So we can say, okay, if you, for instance, okay, add another 5 centimeters. Okay, yes, it's 25 centimeters or 21 centimeters. Clear? Okay. Now the answers that we have here is 1 centimeter, 9 millimeters, 5 millimeters, and 14 millimeters. Now, guys, 1 centimeter. Well, okay, it could have been. Okay. This could have been, yes, okay, where we will have a width of 1 centimeter. Okay. It can't be 9 millimeters because that's what we had at depth of 16 centimeters. We already did that earlier in question number 2. Yeah, okay. It can't be 5 millimeters because 5 millimeters would have been. Yes, okay. You can say yes, okay. Anywhere here. Clear, okay, or anywhere here, for instance. Okay. So here is okay to go by is okay a diameter of 14 millimeters. Okay. But there's nobody who said that it couldn't be 1 centimeter. So I don't know why. Okay, but anyways. Yep. Did you guys get that? Yes, guys.
Yeah.
Okay, good. Thank you. Question number 6. Now, the ability to distinguish two structures lying close to one another is called resolution. We already, yes, okay, had a similar question, yes, okay, when we talked off axial. So resolution as well. Okay, a similar question was asked as well. Okay, so that ability of, okay, yes, displaying, okay, distinguish between two structures lying close to one another is called resolution. Okay, where these structures, okay, are in depth, that'll be axial resolution, where they're going to be, okay, side to side. That'll be, okay, what we call lateral resolution. Question number 7. Now, the ability to distinguish two structures lying close together, front to back, is called axial resolution. Now, we know that axial resolution can also be called longitudinal resolution, range resolution, radial resolution, and depth resolution. Did you guys get that?
Yes.
Good. Whereas the next question is, okay, just ask what we just said here. Okay, the ability to distinguish two structures, okay, lying close together. You can maybe say, okay, or yes, okay, they're asking about some sort of resolution, okay? But here it's okay, it's side to side. So side to side is going to be your lateral resolution, also known as angular resolution, also known as transverse resolution, also known as over solar or stars over solar, azimuthal resolution. Did you guys get that?
Yeah.
Good. Question number 9. Now, axial resolution and lateral resolution are both measured in with the units of distance, because where we said axial resolution, yes, okay, it could still be, yes, okay, millimeters, centimeters, whatsoever. So for your lateral resolution. As a matter of fact, even, yes, okay, the last one, okay, let's go to last, okay. Others, yes, okay. Example of a spatial resolution, which, sorry, this is going to be the elevation resolution. It's also going to be, yes, okay, measured in units of distance. Okay, but here it's okay. They can't ask about that because this is something that we talk about in a later chapter. Okay, all these three resolutions here, is okay, are going to, yes, okay, be measured using units of distance or length.
Bless you.
Bless you.
Question number 10. Now, what they say here is, okay, when the number of cycles in a pulse increases, so we increase the number of cycles in a pulse, right? Okay, while the frequency remains constant. Yeah, okay, so it was, for instance, okay, it was 2 megahertz here, it remains that. But it's okay, we may increase the number of cycles from, let's say, it's okay, 2 to 4. Medina, put it back. Excuse me. Sorry, guys. Okay. So this increasing of the number of cycles is actually, okay, what we can call more ringing. Yeah, okay. So, and what they mean is, okay, says, how is that going to, is that going to have any effect on our numerical value of axial resolution? We can say, if we increase the number of cycles from 2 to 4, for instance, 4 cycles, always, okay, the frequency is the same. That may mean that, okay, the wavelength remains the same. Yes, okay. The spatial pulse length will increase, and that increase in the spatial pulse length will increase the numerical value of your axial resolution. Did that make sense? Okay, and this increase in the numerical value of the axial resolution will cause the axial resolution to get poorer. Okay, now here's, okay, in the question, although it's okay, they didn't use the word axial resolution, but rather range, but just tells you, it's okay, that you got to know the different nicknames of your resolutions. Otherwise, you will be lost. Okay. Had it been the same question that says, okay, when the number of cycles in a pulse increases while the frequency remains the same, okay, the numerical value of, and if it has said anything about it, okay, ask about your lateral resolution, then it will remain the same. Because your lateral resolution is not determined by the number of cycles in a pulse. Did that make sense?
Yeah.
Right, okay. Okay. But again, yes, okay, the term lateral resolution could be, yes, okay. We could use something like, okay, as angular resolution, we could use transverse resolution, or we could use azimuthal resolution. So again, yes, okay, if you don't know that these are just different names of your lateral resolution, again, you will be lost. Now, of course, yes, okay, you have to know the relationships as well. Question number 11. Now, when the number of cycles in a pulses increases, okay, and here's okay, the units, okay, yes, okay, so increase in the number of cycles, and I just said earlier, yes, okay, that's what we'll end up calling more ringing. Okay, while the frequency remains the same. Yes, okay, frequency is, we can say, okay, unchanged or remain the same, right? Okay. The image quality improves, degrades, or remains the same. That's okay. I don't like the word image quality because quality doesn't really, yes, okay, specifically means the same as the resolution. But that's probably okay what they meant here. Okay, okay. So, okay, so yes, okay. Does the what's going to happen to the image quality, or more correctly, resolution? Yes, guys, it will degrade because the greater number of cycles causes more ringing, which means increase in the spatial pulse length, or the increased numerical value of the what do we call it, of axial resolution, which we'll call it to degrade. Did you guys get that?
Yes.
Good job. Question number 12. Now here they're asking, yes, okay, a high or low frequency transducer has the best range resolution. Now, even before getting into that, what is the range resolution? An axial resolution, radial resolution, and depth resolution, and longitudinal resolution. So which of these will have the best of this resolution? Was the one with the higher frequency, because higher frequency means lower wavelength, lower SPL, lower numerical value of these resolutions, which will mean that it should be the best. Did that make sense? And that's why I said back in the chapter is that high frequency transducers are ideal for diagnostic imaging. But high, yes, okay, great for high frequency. Good is good, but then too much good is bad. Why is it going to be bad? Because too high of a frequency of a transducer is going to cause too much attenuation, and you won't have. And if that's the case, then there will be no image. Okay? If the sound wave dies even before penetrating or traveling into the tissues, forget about getting a reflection, right? Okay, and if you don't get a reflection, forget about it. Okay, amplifying all those, they are not going to give you anything. Did you guys get that? Good. And what is it that frequency is? Yes, Dr. Tolson, that will be for you. What was it that frequency was? What's frequency? Okay, let me ask you. Is frequency a variable or is it a parameter?
Parameter.
Parameter, okay, good. In context to attenuation, is frequency a factor or a process?
It's a factor.
Okay, good. Okay, what were the processes? Anybody? Anybody? What were the process of, yes, Maria?
Absorption, reflection, and scattering.
Scattering. Those are processes. Okay, okay. Good. Now name 4 synonyms of axial resolution. Axial resolution, longitudinal, range, radial, and depth. Are the other nicknames or a cause of your axial resolution? Okay, guys? So name 3 synonyms of your lateral resolution. We just talked about them earlier this morning. Right, okay. Angular, transverse. Because if you look at the relation between them, that's how I remember it. The relationship between the main axis of the beam and the structures. They form a cross, which is going to be transverse. And last is azimuthal. Just think that, okay, a lateral resolution will throw you into the stars. Okay, good. Question number 15. Let's look. A lot of numbers. Let's see if we can. Okay, now, guys, okay. One other thing, because most likely, yes, okay, on tests, you may not get a diagram. as we had, for instance, yes, okay, in figure 10.11 that we just looked at, right? Right, okay, so you may not have a diagram. So some of you will say, so how in the are we going to just, okay, get question about things such as, okay, letter resolution or something like that? They were numeric, they were actually just, okay, try to explain the diagram in terms of words. Right, okay. Have you guys ever wondered why was it that parents would use to read as, okay, a bedtime story? What did that do? And especially as, okay, fairy tales with castles and whatever knots and so on. So if you recall those fairy tales, what did it use? Yes, okay, that was used to be this princess and she lived in this big castle. And okay, what is it that you would be doing in your head?
Imagining it.
Imagining it, or yes, okay, trying to picture it, right? Okay, so that's mainly as, okay, you have to use that similar skill here. Okay, to try, yes, okay, try to, yes, okay, pick up the information that's going to be enable you to, yes, okay, picture this whole thing. Okay, so let's just do this together as we read this question here, right? Okay. Good. So the length of a pulse is 8 millimeters. This is your pulse. And for instance, okay, he or she is 8 millimeters. Okay, that's all. Okay. Anyways, so let's see. What is the minimum distance between two reflectors positioned in front and back to one another that still produces two echoes? Now, the only thing that you need to, you know, this is the length of your pulse. So that means that length of pulse is 8 millimeters. Okay, so this was not one of those questions. That's what the mean is, okay, just ask, okay, what's going to be the minimum distance between two reflectors, one front and back, where we still will, yes, okay, see these as two separate reflectors on the image. It is going to be the one in front and back. So mainly as, okay, what the mainly as, okay, did why it is, okay, front and back is asking about, can you calculate the exit resolution? Numerical value here. And that's straightforward. That is just your 8 millimeters. Divided by 2, which is going to be 4 millimeters. So the answer here would be that as long as this distance here was at least 4 millimeters. These two structures here will be showing us two separate reflectors. Okay, but guys, if you just look at figure 10.11, okay, which was, okay, as what we used to, yes, okay, do the first 5 questions. So how will we actually, yes, okay, be able to word this diagram here? Okay. Okay, that's all that's okay, the diagram here, but let's just do the opposite. Oops, sorry. Let's just do the opposite and word the question. So you may say it's okay that they say it's okay. You can say it's okay. You can say it's okay that you have a transducer. Now, usually, guys, that's okay. What you will realize is, well, yes, okay, when we go to, yes, okay, a later chapter. Chapter 12, that when you see, yes, okay, PCT given like this, you have a transducer with a single PCT. Okay, that you have a transducer with a single PCT. Now this single PCT here is okay, can also is okay later on be referred to as a, that they will say that you have a mechanical transducer. Okay, but what we mean is I can say is that this single PCT is okay, has a diameter of 9 millimeters. Yeah, okay, that's one thing that we saw in the diagram. Yeah, okay. The next point that we as okay see in the diagram is the focal depth is 8 centimeters. Did that make sense?
Yes.
Right, okay. So this will actually is okay, you can say B is okay, verbal format of figure 10.9 or 10.11. And then they can go, and then we can go on and say, okay, what is the lateral resolution at depth of 8 centimeters? Okay, what's the lateral resolution at a depth of 16 centimeters? Papa, pee pee, poo poo, all that. And okay, as your questions from 1 to 5 can mean, yes, okay, just be following here. Did that make sense? So although I said that, okay, as you most likely won't be getting diagrams, okay? If you do, just take that as a blessing or, yes, okay, of course, whichever way you want to look at it. Okay, okay. But yes, okay, keep in mind that, okay, yes, a diagram can also, yes, okay, be explained verbally. Okay, so yes, okay, from the words that we just did here, yes, okay, you can say, okay, this will be, yes, okay, what a diagram that you made, yes, okay, you can make on your rough piece of paper. No Mona Lisas. Okay, none of you submitted, yes, okay, the Mona Lisas or theories or thesis that you wrote yesterday, right? You may, yes, okay, toss that paper into the trash. Okay, guys? So, yes, okay, most likely, yes, okay, the question that we have in the exam reviews for chapter 9, 10, sorry, chapter 10, right? Okay. Now, guys, this will be your homework. Let me put this, what will be your homework? Reread chapter 10. Please make sure that you understand every little bit of it. Clear? The next thing will be, yes, okay. And that's okay for this chapter, yes, okay. They have me, yes, okay, jumping a little bit around. But it's okay if you know how it works by how this book here. So it's okay for your Excel resolution. You can mean it's okay, go just okay from to page 477 to page 480. Or rather from, yes, okay, question 257, no, 258, sorry. To question 274. Okay, these made, yes, okay, were requested about, yes, okay, your Excel resolution. Whereas, here guys, for your lateral resolution. And then you says, okay, things such as focusing. That's fine. But what do we have? That's okay. You go to page 492. To page 496. Or question 328 to question number 349. Did you guys get that?
Yeah.
Okay. So now before sending you guys off, any questions about the anatomy of the beam? Any questions about anatomy of the beam? Factors determining focal depth. Factors determining beam divergence. Relationship between size of PCT and diameter of beam at the focus. No. Good. So if you guys understand the anatomy of your beam, you will understand your lateral resolution. Okay, guys? Then enjoy the rest of your day. Have a nice weekend. And stay warm. Don't get sick. And take care. Okay, guys? Okay. Any question? Yes, okay. If it's really pressing you, that's okay. You can always send me an email, okay? Asking. If you want to, okay, let me just ask it when we get to the class. Okay, that's fine as well. Okay. So yes, okay, this is okay, a little bit a project for you guys. So Monday, yes, okay, we can look at the questions and we can go on to the next chapter, which is a relatively, yes, okay, very small chapter. Some of which I already, not really, but okay, slightly, yes, okay, displayed to you guys on the machine yesterday. Okay, or modes. Clear? Okay. Okay, guys, then I guess I will see you later, guys, on Monday. Monday's not off, right? Not a holiday yet. Okay, guys. Have fun.
Have a good weekend.
Have a good weekend.
Have a nice weekend.
Okay, bye-bye.